once to major in physics, but then I researched how much you need to like how much material you need to understand to be able to understand some deep topics, and I opted out of it.
Hmm. Well, maybe that will change if Sami Kaya can persuade you with his slideshow today.
Still not
Well,
too
the
late.
microphone, I'm handing the microphone to you, Mohammed Jamal.
Thank you. Before we begin, Mr. Sami, could I ask you a couple questions?
Sure, of course. Yeah, also
Um,
during the time, feel free to ask questions whenever you want.
okay. What made you
Yeah,
want to study physics in general?
that's a great question. So yeah, when I was in high school, I was studying like college level physics for like physics competitions back in Turkey. And I realized that I enjoyed it very much. And I just wanted to keep going, keep studying that, in college too. And then, I've been studying physics ever since. And like there are very interesting questions out there, very um like the questions about the functions of the universe. And I think it's very interesting to think about those things.
And one more before we begin. Why are black holes so complicated to research or understand about?
That's a great question. I don't think so. Okay, there is a short answer and a long answer. I guess the short answer is we don't understand them very much. We don't understand gravity when it becomes that strong. That's the short answer. I guess if I want to go a little deeper into it, there is things that are fundamentally um like there's fundamental things in quantum mechanics and gravity that kind of conflicts. That's not it's difficult to merge them together, and
Mhm.
it becomes manifest. Black holes are a very good example of when these things manifest themselves. So that's why we study them. That's why we try to understand them better. And yeah.
Yeah, thank you. I have no further questions.
Cool. Yeah, so I can get started. Okay, yeah. So today we're gonna be talking about gravity and black holes. We don't have that much time, so most likely it's going to be very, very introductory stuff, and then I'm going to introduce black holes, and then that's probably going to be it. Everything's going to be classical, nothing quantum mechanical in this talk, most likely. And yeah, so I guess a brief disclaimer before I start. This is a very brief introduction to very complicated physics, right? So a lot of things I say are going to be heuristics. They're some of them are not true, might not be true in technical rigorous level. But yeah, so like don't yeah, take everything with a grain of salt. But like everything is gonna be nothing is rigorous in this stuff, I guess. Right. Okay, so let's start with doing an experiment, right? I'm gonna describe the experiment to you, and then I'll ask you what do you think the result will be, and then I'm gonna tell you what the result is, right? So as you can see, we have two people, right? A person in a car. The person is standing stationary, has a flashlight, and
Mhm.
he's flashing a light to a wall that's distance d away, right?
Mhm.
And in the other picture, we have a car that's moving with the speed towards the wall, right? And at that time, when the photograph was taken, they're standing at the same exact position. They're d distance away from the wall. So the light that comes from the flashlight from the cop who's waiting there and from the car, what do you think their time of reaching the wall would be? Would they
Uh,
be the same? Would they be different?
if the car is stationary, from
The
what
car is
I
moving towards the wall.
oh yeah, then
The guy is stationary.
then like through common sense, the car's light should move faster, but wouldn't they still be the same regardless because speed of light does not change?
Exactly. Yeah, that's the point. So if there was something else, like if a person in the car was throwing a ball towards the wall, or the guy was throwing a ball towards the wall, you would expect the ball would go faster if you're in the car because you're moving towards the wall. But the universe has a speed limit, right? Nothing can go faster than the speed of light. So it turns out in both cases, the light has a constant velocity, which is what we call c, right? And it would take the same amount of time, whether or not you're moving towards the wall or not, right? So
Mhm.
that's like the speed limit of the universe. And the people actually did this experiment, and they saw that speed of light doesn't change, right? It's a constant.
Is
Good.
there any way for us to like ever overcome the speed limits
No,
and survive?
yeah, it's a
Okay.
very fundamental limit. You can't go faster than the speed of light. Like us, so for you to be able to go at the speed of light, you have to be massless, right? For
Mhm.
us, it's not even like it's a strict limit. You can't even, yeah.
All right.
Okay, so that was an actual experiment. Now I'm going to describe a thought experiment. Actually, this thought experiment was basically what led Einstein to derive his theory of special relativity. It's a very, like, I guess in that way, crucial thought experiment. So we have a train car, right? And we have mirrors attached to this train car, one at the top, the other one at the bottom, right? And we have a laser, and we reflect light back and forth, right? In these two mirrors, one at the top, the other one at the bottom. So in the first case, in the first picture, as you see, we are in the car with the light, right? And we go sit up and down, right? We measure some time. We see how long it would take for the light to go one up and down. That's the time measured. In the other picture, we are outside of the train car, and the train car is moving, right? As you can see in the first picture, the distance traveled by the light is like as it goes up and down is shorter than the distance light travels in the second picture, right? Because it has to go all the way across and then come down again, right? It's a diagonal. If you remember, the speed of light is constant, right? And the distance traveled is just the speed of light times the time that it takes for light to travel, right? You see that since distances are different, the times are going to be different as well, right? So
Yeah.
this is basically the concept of time dilation, right? The time experienced by the guy in the cart and by the guy outside of the cart is going to be different, right? They're going to experience time in a different way. So just from the basic fact that the speed of light is a constant, you can get to time dilation by a simple thought experiment like this, right? And I guess of course it's always like more technical than this, but this was kind of Einstein's starting point. And after this, he developed his theory of special relativity, which is basically incorporating into the theory that speed of light is a constant. You can re-express physics in ways that's not coordinate dependent, right? Like, for example, time in this case can be experienced differently. Laws of physics should not be experienced differently. So you can formalize them in a way that it's not dependent on who's observing it, right? That's what Einstein did with special relativity. So that's, I guess, like the first part, right? We know of another thing Einstein did, which is he has a theory of gravity. They're actually connected. Special relativity and his theory of gravity, which is called general relativity, they're connected. Special relativity is a special case of general relativity without gravity, right? So when you don't have gravity in an Einstein's gravity, you get special relativity, right? So I'm just going to describe another principle that led Einstein to his theory of gravity, right? Which is the equivalence principle, which tells you that, like, if I was to say it in a sentence, the gravitational mass and the Newtonian mass are the same, right? But what does that mean? So if I was in a box and I closed everything up, right? Like I can't see outside, and I'm experiencing some acceleration. Like I'm standing, I know that, for example, if you're in an elevator, if it's moving up, you can feel that you're moving up, right? There's a sensation, you can feel the force from below your feet. In one example, I'm just on Earth standing, right? I'm feeling some acceleration because I have some weight. And in the other case, I'm in space. The box I'm in is accelerating with some acceleration, right? That's equal to actually the gravitational acceleration on Earth, say, right? The equivalence principle tells you that you cannot distinguish these two cases. They feel the same, right? So the gravitational mass, like F equals ma, the mass there, is the same as mg, right? Sounds very simple. Maybe it's maybe you could say that this is very obvious. Like, why is this a principle, right? It turns out there's a lot of deep connections to actually what the gravity does, how gravity works, and they all connect back to this basic principle. That's why I wanted to mention it. To see that the connection is not that obvious, I can mention that it took Einstein about 8 years to come up with the theory of like the general relativity after he formulated special relativity, right? Like it took him 8 or like around 10 years to incorporate in his theory gravity, right? So it's not easy at all. It's not obvious at all. Right. So let me talk briefly about Einstein's equations. By the way, yeah, interrupt me whenever you want. If you have questions, I'm just rapid firing right now.
I have 2 questions
Yeah.
I came up with right now. Are thought experiments like very common in modern day physics, or is it just like was this like something that they did back in the day, not very common right now?
So that's a good question. So I guess yes and no, right? There are very fundamental thought experiments. Well, right. Let me just say this. So I don't know about how common they are because they're very hard to formulate. Like it's very hard to formulate useful, insightful thought experiments, right? Like because in the end, they are very simple and they give you a lot of information about how the universe works, right? But there are still very important and insightful thought experiments done to this day, and like formulated to this day, and they give like for example, black holes. They have a lot of like we can't really test anything about black holes, right? Like experimental, they are very inaccessible because I guess we don't have that much control over how strong we can make gravity, right? And how high up in energy we can, like there are experimental limitations. And at that point, the most important tool you have is thought experiments, right? And then one thing that's very important when you're formulating thought experiments is that you're checking consistency, right? If you have a thought experiment and you have some assumptions, they can imply something, and if you want that thing to be true, that's true, right? Like I guess it tests consistency of your theory.
Okay. Yeah. And why does it why does it take so long to create like consistently true physics formulas? Like we know like E equals mc squared, from what I have found out, took like Einstein 10 years to formulate.
It's equals mc squared is more like special relativity, but yeah, like it took him about 10 years to generate, like formalize his. The reason for this is he had to learn the math, right, for to be able to formulate this thing. Like this the formula you see, like this is the equation, right? Like from this equation you can derive a lot of other things. It's very elegant, very beautiful, but the math behind it is very complicated, right? So he had to work with mathematicians to actually learn this math and then apply it to physics. But I guess I would say that's not the main reason why it's so difficult to like do actual physics today. I think there is like things we don't understand very well and things we like, again, I think it goes back to the main thing about like there's conflicting things in not conflicting, but there is principles in quantum mechanics and general relativity that they don't like to work together, right? We're trying to force them to work together. We're trying to find a way to make them work together that would make everyone happy. But yeah, it's not so easy to do.
You could say like they're the two opposite poles of a magnet. So like no matter how much you try to put them together, they don't connect.
Yeah, there's like, I guess you have to give something up, right? Like if you can't really have everything. That's why we have like some thought experiments that tells you, like if you want this to be true, you want this to be true. If those two things are true, this third thing would also be true, but you also don't want that. So you have to modify something. That's why like thought experiments are very important. Yeah. So if I was to summarize what Einstein's gravity is, right? It basically, you can think about space-time as a fabric, right? You guys probably heard of this before. You can think about it as a fabric. Matter on top of this fabric tells it how to bend, right? And the bend, the curvature, the curve of the space-time tells matter how to move. So they're coupled in that way, right? They go back and forth. That's why actually these equations are very complicated, right? Like in the end, they look very elegant, but yeah, mathematically they're very complicated. So I guess two fun facts. One of them is that like when Einstein came up with this theory of relativity, the theory of general relativity in the beginning, there was mixed reactions from the scientific community. Some people were like, hell yeah, this is very elegant. It has to be true, right? Because it's like very mathematically beautiful. And some people had the exact opposite reaction. They were like, okay, this is very mathematically beautiful. This is very elegant. Sure, but that doesn't tell you anything about, we shouldn't believe this more because it's mathematically elegant. We have to test it. Like we don't, nature doesn't have to be elegant, I guess, right? In their point of view. It turns out this general relativity is very true, like very accurately true. So I guess that maybe tells you something about how nature works. Another fun fact is, yeah, actually this goes back to the slide after. The discovery of black holes. When Einstein actually came up with his theory of general relativity, he didn't believe there could be analytical solutions to it. Right? He thought you could do some computations in a computer, some numerical calculations, but he didn't think there would be a solution to it. You can just write down a piece of paper and would describe the solution. Right? That's what analytic means. However, Schwarzschild, right? This guy, while he was fighting in the First World War in the Russian front, he was doing physics, right? Because he's a physicist at heart. He comes up with the solution that is super analytic, super simple. Is the first solution to Einstein's equations that is like simple analytic. While he's at war, and that it turns out later on we discovered that they actually correspond to black holes, That's how I guess you could say black holes were discovered in the First World War. And actually, yeah, like you can see him as he says, like he in his letter to Einstein, he says, "As you see, the war treated me kindly enough, in spite of the heavy gunfire, to allow me to get away from it all and take this walk in the land of your ideas." Right. So, amazing guy. One of my favorite fun facts in physics. Yeah. I feel like you might have questions, but feel free to interrupt. Yeah. All right. Okay. Moving on. Right. Now we're getting slowly to black holes, right? Again, I'm gonna share another factoid, right? Which is that gravity affects light as well, right? That might be a little bit counterintuitive. So like because you see when you throw a ball, you see it coming down, right? But when you fire a laser up in the sky, you don't see it coming down, right? But also you can say force needs like gravity needs mass to act on stuff because you have the formula here, G m1 m2 divided by r squared, right? If light doesn't have any mass, how does gravity pull light, right? How does it have an effect? Well, there's a very crude way of seeing how it can have an effect, right? Because F equals ma, and we know the Newtonian mass is equal to the gravitational mass. So you can write down this quick equation, and the masses cancel, right? So even if the mass is zero, which is the case for light, you can have gravity can have an effect on light, right? Good. Which brings us to the concept of escape velocity, right? So escape velocity is the velocity you need to escape the orbit of a planet or like any massive thing. The idea is that you throw an apple, right? The faster you throw it, the higher up it will go, right? And there is a certain velocity at which if you throw it, it will never come back down, right? It will escape the gravitational pull of the Earth and it will go up in space, which is actually what happens if we have like when we fire rockets up in the sky, right? Now imagine, right, gravity becoming so strong, right? Even the speed of even light, which has the highest speed, like which is the speed limit of the universe, right? Nothing can go faster than it. It can't escape this gravitation, right? What would happen in that case? And the answer is black holes, right? What are black holes? Black holes are just very concentrated masses near which gravitational pull becomes so strong even light can't escape, right? That's what black holes are. So when stars collapse, they concentrate their mass in a very small scale, and if you get very close to it, then you get sucked in. There's no other chance because even light, which is the fastest thing in the universe, can't escape.
Being
I put
about
this, yeah.
Sorry, I cut you off there.
Yeah,
But
yeah, go.
speaking of
That's
escape
completely okay.
velocities, going back to that, how easy is it to reach an escape velocity to like get out of like a planet's orbit or gravitational pull, and can be done like consistently without like any repercussions?
I think it's fine. The only thing is like why is it you can ask why is it hard to like fire up rockets in the sky?
Mhm.
It's because you need a lot of energy, right? So if you could, the problem is energy, right? So it's a certain velocity, and for example, to fire a rocket, the mass is very high, right? The mass of a rocket is very high because it has to be in a way because it needs to carry the fuel as well with it as it's flying up, right? So the energy you have to put in, give the rocket to reach that speed is a lot, right? But say for like, you know, for a light particle, for a photon, it's very easy, right? Like it just escapes Earth no problem, right? Or you can also like if you have the smaller the masses, the less energy you would need. That's why it would like it would be easier to escape Earth. But again, like the problem is mass and energy there.
And also, how are like right now modern images taken into like so far into space? How did they come out so clear? Because they're going like millions of light years into the universe and taking like images as of like they're taken by like the best camera with.
Yeah, so it's instrumentation, right? Like there is a lot of engineering done. So the idea is that the photons they come from space. Like if they haven't interacted with anything, it's like if when it reaches your detector, the signal would be very faint, right? It would be very, very so people engineer ways to actually gather these signals, right? That's why we have like noise is very important in this case. So that's why we send telescopes up in the sky so that, you know, it doesn't get affected by the atmosphere. And then like they find ways to amplify these signals, right? There's actually like it's magnificent engineering that makes it possible.
It comes out. It comes down to the engineering. Yeah. Thank you.
Yeah. I mean, I wouldn't say it's all engineering. It's just like very fine-tuned. Like it's very
Yeah.
difficult to do. Yeah.
Oh.
I wouldn't know much about it because I'm a theorist, but you know, it's yeah.
It's more
It's awesome.
applied. It's more applied.
Yeah, definitely. Yeah. Cool. Yeah, I put this quick slide here because, you know, recently there was some like studies done photographing black holes. You could ask, even if light can't escape it, you know, how would we take a photo of a black hole, which is like, you know, just collecting lights coming from it, light particles coming from it. The idea is that they don't collect light coming from directly from black hole, but there's stuff around it which, as it's like rotating around the black hole before falling in, heat up a lot, and like they also like glow in that way. That's what we are taking a picture of. So in this picture, the center black thing is the black hole. The thing around it is actually the things that are falling into a black hole that are like so hot that they're glowing. Okay, that's how we take pictures of black holes, which is a very, again, incredible feat as well.
Instead of using the normal light spectrum, could we use like either infrared or ultraviolet to try and get like better, clear images of black holes, or is it just like all light spectrums are the same?
So I think it depends on how the thing falling in is like glowing, right? I think it would be, well, I don't think this is visible light I'm not sure, but I don't think you can, it's this visible. Yeah, so I think this is like going into some other wavelengths as well, even though like I'm not sure about technicalities. Yeah. All right, another question for you. Ready? So what would happen, right? So we have Earth rotating around the sun, which has a certain mass. What would happen to the Earth if we took the sun, right? Like we replace it with a black hole with the same mass? What would happen to the rotation of the Earth? Would it change? Would it like go far away or get closer to the black hole? What would happen?
If the masses are the same, shouldn't the gravity would also be the same? Shouldn't like the
Exactly.
gravitational pull be the same? So nothing would fundamentally change?
Yep, exactly.
Ugh.
That's exactly right. Yeah, you're a good host. Yeah, so since the radius is the same, right? The formula stays the same. It's G m1 m2 divided by r squared. So the radius is the same. Both masses are the same, so nothing changed, right? So the rotation of the Earth would be the same. The intuition sometimes people have is that, you know, black holes pull things, you know, even light, they pull it, right? So like the Earth would get sucked in as well, right? But the reason why black holes are like so powerful in terms of like sucking in stuff is because they're concentrated in very small volume, right? So it's that you get, as you get closer, r squared becomes smaller, the force gets bigger, right? For sun, there's a certain radius you can come up to, right? Like you can't get closer than that because then you would enter the sun. For black holes, since they're like concentrated in a point, you can get arbitrarily close to them. That's why the force can be arbitrarily high as well, so that, you know, even light can't escape it. But yeah, like if you are a certain distance away from a black hole, you're completely fine if you don't get close to it. Good. Right. So let's talk about this specific fun thing in physics as well, and then I guess I'm gonna end with this. So the question of falling into what happens when you fall into a black hole is actually more complicated than it would seem. But again, classically, if we're just doing classical physics, Einstein's gravity, there's a name for what would happen if you fall into a black hole, which is it's very hard to pronounce. It's called spaghettification, right? The idea is that the forces as you're falling into a black hole would behave in a way that would make you like a spaghetti, and you would elongate, and then you would thin out, and then you die horribly. But the part of like getting thinner and then, you know, elongating is called spaghettification. You might ask why that is, right? It boils down to the idea of tidal forces, right? So as you're falling into a black hole, the amount of which the black hole pulls your feet down is so much different than the amount of which it pulls your like torso or your head down, if you're falling in like this, right? It's so different that your torso can't catch up to your legs.
Okay.
Right? In the end, your legs would get away from you in that way. So you
Your
you
legs
would
would like
elongate
stretch
and then
out
you
then.
stretch it out. Exactly. And that's because like the gravitational force is so strong, and the variations of it so become so different. As you're falling in, you would become like a spaghetti. That's a
So
very
I'm guessing in this like image you have on your slide that white dots or white circle, there is the place in which you said the R value, the radius is one that switches and starts to get bigger instead of smaller.
Yeah, so I guess in this picture the white thing is like right outside of the event horizon, which is basically the point of no return, right? Like if you get closer to the black hole than that, even light can't escape. That's like that radius. I think that's what described over there. But yeah, I guess that's called the horizon of the black hole. If you hear that thrown around in the media, that's like the point of no return. If you get closer to black hole than this, you cannot escape.
So I'm guessing no matter like no matter how much like humans evolve or like engineering becomes better, there's there's no possible way for you to escape spaghettification the moment you enter the event horizon.
Yeah. So the point is a little bit, yeah. Like what exactly would happen is a bit different. Like it's a more complicated question because we don't exactly know because there's quantum effects that come into play. But the idea is that yeah, like it doesn't matter how sturdy you make your spacecraft, right? In the end, first thing, if you fall in, you can never come out, right? So in the end, you will die horribly. But also, like, as you get closer and closer to the black hole, these tidal forces would increase more and more. So in the end, it would make you turn into spaghetti.
Okay.
Yeah. So you cannot. There's nothing we can do to compete with that, I guess, in this level.
All right. Thank you.
Good. Yeah, I'm not sure how I'm doing with time, but I guess we can end here. Thank you for your time. You know,
Yeah.
pun intended.
I
But
can
yeah.
ask one or two more questions, and then we can end with our classical three questions that we ask for each guest at the end.
Yeah.
First
Awesome.
is the universe infinitely big, or is it just like, is it just so big that we cannot like imagine how big it is?
That's a great question. So cosmology is fascinating, right?
Mhm.
To the best of our knowledge scientifically, right? The universe is I guess it also depends on what you mean by like finite or infinite, right? Let me see how I can answer this question. So we can only observe a certain part of it, right? We don't know what happens outside of it. Because you know the fastest thing in the universe is light, and then we can only observe the part where like light had time to reach to us yet, right? That's the part we can observe. But according to our best knowledge, right, there's the expansion of the universe is increasing exponentially, right? It's becoming exponential. So in that way, even if it's finite now, in time, if nothing changes, it will become, you know, like an infinite universe. So it's expanding super fast. But yeah, I guess the physically relevant question is really not the full size of the universe because we can't really observe it, right? It's just the part we observe is expanding exponentially.
Okay.
It's super fast. Yeah.
And before the three questions, what do you think will happen to the universe out of like the three predicted outcomes, which is just like to reiterate, either continue to expand exponentially like how it is right now, expand and then like suddenly like plateau out, or expand, then stop, then shrink and cause the Big Bang to happen again? What are your
Yeah.
thoughts?
So
On
yeah,
that?
you're talking about the closed universe, the open universe, and the yeah.
Mhm.
So it depends. It depends very much on what's in the universe, right? And we're not. It's difficult to know that, right? Because in the past, people thought it was, people like did experiments and guessed that it was expanding and it was going to keep expanding, right? It was going to keep expanding and it would never end expanding, right?
Mhm.
And then at some point, the experiments got better. They figured out that it would expand, and then it would plateau, right? That's like the current state we're in right now. So that's like the flat case. If it was closed, if there was like more matter in the universe or more mass in the universe, it would expand, and it would like collapse back because the gravity would win over the velocity, I guess, of expanding, right? That's like the closed case. And the first one, when it's like expanding and will keep expanding forever, that's called the open case, open universe, right? So that being said, so the current understanding we have is that it's gonna expand, and it's gonna keep expanding even faster, right? So it's the open universe case, even though currently it's very close to being the flat case, right? Like it's expanding, it's about to plateau. And what gives you that, like what we know that would give us the exponential expansion, the keeping expanding answer, is that this thing called the dark energy, right? We observe now the expansion of the universe is increasing, right? It's instead of slowing down, which would be the case for the open and the closed one, which would be the case for like the recollapsing one or the plateauing one, we know that it is actually accelerating, right? And that's due to something called dark matter. Sorry, dark energy. You probably heard of it. If this is called something dark, that's because we don't know what it is exactly. So and we can't see it. So that's exactly what dark energy is. We don't really know. There's some theories. We don't really know what it is exactly, and we can't really observe it directly with light. That's why it's dark energy, right? And it has some properties that lead us to call it energy. But yeah, I guess the short answer is that our current understanding is that the universe is going to keep expanding forever.
Okay. So thank you for your time. And before we close it off and finish this episode, I would like to ask you the 3 questions that we ask each guest. Number one being, what is your favorite color?
My favorite color, turquoise.
A great color.
Yeah.
What are 3 books you would recommend that our viewers read?
That's a very good question. So can I give like 3 different series, or does it have to be like 3 different individual books?
It doesn't matter. Whatever. It can be
good.
series or it can be individual ones. You can mix
Okay, yeah. So the first series I would definitely recommend is The Three-Body Problem. It's 3 books. It's a very, very good book. It's very good science fiction. There's actually also, I think, like a series on Netflix now too. I would definitely recommend reading the books first. I haven't watched the show, but the books are awesome. My favorite books in the science fiction genre. The second one, I guess this is like if you like books, that end, it's not a good suggestion for you. But there's this it's supposed to be a trilogy. It's only 2 books out, and the 3rd book hasn't come out in a while. It's not certain that it will ever come out. But it's The Name of the Wind by Patrick Rufus. Awesome fantasy. I would definitely recommend. And I guess the 3rd one is also, I guess, like in the fantasy genre. Very, very good book. Again, it's 3 books out. The 4th one is about to come out, I think, but I'm not sure. The Lives of Laka Lamore. Awesome. Definitely recommend. Yeah.
Thank you for the recommendations. And for the final question, what is a movie, film, documentary that you recommend that people watch?
That I recommend. Okay. Only one? I got 3 books and 1 movie? Okay.
We can make an exception. You can say one.
Yeah.
Well, it's like the most important one that you would say, and you can give it like a list, so like number 2 or 3.
My favorite movie ever, I think, is Inception.
Okay.
So I would definitely recommend watching that. It's a great movie.
Great
I
movie.
guess to stay on topic, I will say Interstellar. That's also a great movie. Like I said, could have been one of my favorite movies. Except for when spoiler. I don't know if it's a spoiler, but when they fall into the black hole, it becomes no longer scientifically accurate, which bothers me. But yeah, up until that point, the movie is awesome. It's very scientifically accurate. They actually talk about some of the concepts we talked about today. They touch time dilation in a very good cinematic way. So we definitely recommend.
Are there like any other ones that you would recommend except Inception and Interstellar?
There's a lot of ones. We can talk about movies for a while, but yeah, let me stop now.
Okay. Well, we appreciate your time, and
Thank you so much for having me.
I think